Hello again, ladies and gentlemen. My name is Chiravachradej. Today we'll be discussing how we calculate deformation caused by bending moment in beams using the technique we call virtual work. The reference I use, and some picture will come from this reference, is again the same book like last lecture from Hebrew, the one that is printed in the year 2000, the 4th international edition. The topic for today is the needed background as usual. We discuss what we need to know before we took on the venture of the virtual work. Then we will discuss about the principle of the virtual work. Then we discuss the virtual strain energy, or sometimes it's called internal virtual work. Then we'll see how we apply this concept into calculation for beam deformation. Before we start on this one, we need to understand the concept of external work and the strain energy, which is covered in the last lecture. Also, that will cover up to the point of conservation of energy too. Then we have to have the good grasp of the idea on how the structure, in this case maybe just a beam, how does it deform, how do they deform under pure bending moment. Then because this one here will involve a lot of function of the bending moment, therefore you need to be able to determine them correctly. Let's look at this picture here. Okay. This picture here is any body. This picture can actually come from the book that I quote at the first. This body is subject to an imaginary force. I have to say imaginary, meaning this force is not real. Okay. So we're going to use that force. Well, it's acting at point A. But what happened at point A, we'll try to discuss about it a little bit later. But at this point in time, we apply this force, P1 star. The force equal to 1 star. The asterisk, the asterisk, so that we can keep in mind that whatever end with having asterisk as the superscript is not real, it's imaginary. At the end of the day, we want to get rid of it from our equation. Okay? Now, this imaginary force, although does not cause any displacement, it actually causes the imaginary internal force, imaginary stress basically. Okay, and it is shown by this choosing small element here. Okay. This one here is just representative, meaning the U star will be all over the body. The U star is what I meant by the internal force, but imaginary internal force. Okay. Now, this body also doesn't not yet deform, basically. Now, however, we will subject this body into real forces. In fact, maybe even moments, anything, right? Just anything. Oh, hang on, I forgot. Then the work done, I'm coming too quick. Okay. Now, if the body, as I said, was deformed by other external forces, this P1, P2, P3, and maybe many more are real forces. So the picture at the middle here, well, the left hand side, the middle, at the middle here is real force and real deformation. Now, the point A, of course, assume that it moves, okay, and point A will measure the movement. Notice my wording. We will measure the movement of point A on the same line as our imaginary force 1 star. So this line of delta, okay, we measure on the same line of this one star, the same line. And of course, that small element starting having the length of L, of course that one U star doesn't cause any displacement, therefore there is no extension there. However, with these forces, then that extent does become bigger. Okay, then let's look at the work done here. Of course, in this picture here, although we did not draw the imaginary forces, but actually P1 star is still here, then move to here in the same line as delta. Okay, U star starting from here, then move here as well. That delta L, that DL, sorry. Therefore, the external work done, the imaginary one, again the asterisk suggests that this one is imaginary. That external imaginary work done therefore must be equal to that force times on the same line that delta. So the force times the delta. If we think of what we have done last lecture, this one here is not, the one star is not the one that caused the displacement. One star is the carry-on force, meaning it just stuck there and moved with the point. Therefore, one star is a constant, it doesn't increase or decrease with delta. Therefore, the work done here, or the imaginary work done here, is in fact the force times the distance. One star is the force, imaginary force, times delta, the real movement. Okay? Now that is the external. The internal, okay, for this element alone, that U star moving from here to here, the total distance is dl, okay, but that is only one element. If we want the whole body, then because we assume this in the form of discrete, okay, therefore we use the symbol summation. Well, summation and integration is the same thing anyhow, meaning the combination of all. Okay. Therefore, the work done inside the material, or in fact this is the strain energy stored inside the material, can be derived in that form. And of course, with the conservation of energy, although this one here is imaginary work done, the conservation of energy should still exist. Therefore, there can be written in that form, meaning the imaginary external work is equal to the imaginary internal work done, or strain energy. Now, if we continue to analyze the strain energy, the virtual strain energy, of course, and if that star, rather than thinking about the force as thermal force, we can actually put in as a moment as well, and this time of course the work done will be measured by theta. Okay, basically all the picture will be just the same, just changing the one star form force to moment and change delta, align displacement into how the body would rotate, but the rest is the same, therefore expression is the same. Now, if we carry on to see the virtual strain energy, the way we solve it will be the same way we actually solve using when we find the elastic strain energy, the real strain energy. Okay, and we can derive for the axial force in this form. Okay, and then in this form. Again, the word integration, the symbol integration and sigma is the same thing, meaning combination of all. Okay, this one here suggests that n star, remember? Oh, sorry, this expression is a bit too long. We don't have L in here. We have n star n dx over EA. Okay, I will change that for your lecture notes. But anyway, that n star, that one comes from the virtual force. That one n has no asterisk. It is real force. Where does real force come from? It comes from the real strain. Remember the way we derive it? Same here. That one is from imaginary force or moment. That one is from the real force and moment. That one, of course, the material property and the cross-section property. Okay? Let's see how it works, shall we? I think with this idea so far, it's probably a bit confusing. So let's look at some examples so we see how we apply it. Okay? Now, let's look at some simple example. Okay? Now, this is just a cantilever beam. Okay? This wheel load is stable and the one of VI is constant. Now, let's ignore everything or other deformation. Well, in this case we have only shear and bending moment deformation. Let's ignore deformation by the shear and let's focus on the vertical displacement and slope at point A. Of course, this means it only caused by the bending moment. Okay, then let's look at the equation we have. We have the two things. Okay, if we want to talk about displacement, again they said vertical displacement and rotation and slope that we have to find, right, at point A. Now, if we want to talk about the displacement as a line, then we have to talk about this expression here. Okay, if we talk about rotation, slope, the change in slope, of course, then we have to talk about this expression here. Now, the term on the right hand side here, in fact, derive from the same term. Okay, the real force. Okay, imaginary but virtual strain energy. Okay. Let's talk about it in two steps. Let's talk about how we're going to find vertical displacement. Okay, this is the idea. The idea is that this is the concept. You apply the imaginary work done, imaginary force at the point you want to know displacement in the direction of the displacement, right? So we want to know displacement of point A in the vertical direction. Okay, now this one here we just put in. You can put one star upward or downward, doesn't matter. Okay, just put it there. What we know is that we want to know displacement at point A, vertical displacement at point A in the vertical direction, of course. Therefore it has to be up or down and it has to be at point A. Now, remember the equation. When we actually use the equation, we are not using one star though. What we use U star, the internal force, the virtual internal force. So we have to find out what is our virtual internal force. Okay, how do we find it? Of course, we cut section. In this case, of course, we're talking about bending moment, right? Then remember the BM star. So we have to find the bending moment caused by this imaginary force. Well, just cut section X and then using equilibrium, then we can find that, we can realize, we can generate the expression for the virtual bending moment, the bending moment that is not real, again with a star. Okay, the expression has BM star times BM. That big BM is real bending moment. Therefore, we go find the real bending moment in this picture. This picture here, okay, said that displacement, which we will turn into strain, and then we turn that one into stress, that strain into stress, and then link the stress back to the bending moment, remember, and then we get the expression for the bending moment. So in the end, we want, notice that as I stated before, P1, P2, P3 are real forces. So we are looking at this scenario, the same body subjected to real forces, in this case W, distributed load, real distributed load W. Okay, how do we get that bending moment? The same usual way. Okay, notice that the last time what we did for the virtual bending moment, we run X from A to the fixed support, meaning from the right hand side to the left. This one should go the same way. It defines the element the same way. It has to be the same element, the same measurement, the same reference. Okay, and therefore once we cut it with that in mind, then we have that picture. Again, running X from A to the fixed support. คราว cut it here, then therefore we can derive the expression for the real bending moment. Now, when we want to calculate the vertical displacement, okay, look at this one here. EI is given, L is given, sigma has no meaning here because there is only one element, one member, one part of the bending moment. Then that one is from the virtual, that one is from real. Okay, therefore combine these two, substitute that into that, the real one into the real one. Okay, and then we have that expressions. Since both are minus, time up become plus integrated, then we have this expression. The argument is that even though this force, 1 star, is imaginary, it is not zero. If it's not zero, it means that for this to equal to this, there's only one possibility. Delta A must equal to that. Okay? There. Now, how do we find which way delta A go? Okay? That one here is clearly positive. Here. Okay? Here. This one here is positive. What is that expression stand for? That expression stands for the work done. If the work done is positive, it means that the direction of the force and the direction of the movement go together. If that's so, the force, 1 star, the virtual force, the imaginary force there, pointing down, for that expression to be positive, meaning delta must also coming down the same direction. There we are. So we can summarize that with the calculation we have and with the knowledge of what the plus minus mean in work done. We can say that delta A is down by that amount that we have just calculated. So we get the first answer. The second answer, we need the angular change, the slope. Now, how do we do angular change? Then the expression is 1 times theta. That 1 star is actually moment. So we apply it into that idea. Okay? We want to know at point A, we apply at point A. Rotation in 2-dimensional has only about z axis, so we don't have to concern much about whether which way we turn. We just have to guess, just put in anti-clockwise the same. Okay, again we want Bm star, the virtual bending moment, therefore we cut the same way we cut before. There, the bending moment expression, again calculated by normal equilibrium. Expression is there. Again we have that one, that 2. Okay, the real bending moment expression is the same one as before. We haven't changed it, it's the same. That one is however a new one, okay, coming from that 1 star. Substitute into the right expression, then we have in that form. Minus times minus again become plus, then integrated. We have that one. Same argument, 1 star, although imaginary, it is not 0. Therefore, delta A must equal to that term. Now, direction. Again, if the work done is positive, this one here is about moment and rotation, meaning the moment and rotation must be rotating the same way. Notice that moment we are talking about, we are not talking about the BM, we are talking about this virtual moment because that is 1 star and that is 1 star, the same one. If that one going clockwise and the work done is positive, it should mean that theta is also going clockwise. And then we have our second answer. That's it. So these are our answer for delta A and theta A. Vertical displacement and the slope at point A. Okay. Let's look at another example. This time here, we're going to look at the simply supported beam. The uniform load is 2W, EI is constant, okay, and of course, of course, the deformation by transverse shear will be ignored, and we use virtual work to determine the vertical displacement and slope at point A, angular displacement at point A, of course, vertical and angular displacement at point A. The equation is the same, so I will not emphasize so much on it, but again, we still have to find what is the virtual bending moment and what is the real bending moment. In this case, it comes, as we see before, as a function rather than just a value. Remember the concept on how we find the virtual bending moment. We apply the virtual force to the point we want to know displacement in the line of the displacement we want to know. The point we want to know is point A, the movement of point A. So we put the virtual force there at point A, the 1 star. And of course we want to know vertical displacement in this case. Well, it's on the heading. Therefore, we have to put that 1 star into the vertical line. Could be up, could be down, doesn't matter. Then we should recognize the fact that with this picture, the bending moment, the virtual bending moment, will need 2 sections of analysis. From 1 to A will be one virtual bending moment function. From 2 to A will be another, or A to 2, 2 to A, will be another virtual bending moment function. Okay. Nevertheless, the step is, as we have done all over again, find reaction first, equilibrium of course, then look at the first part from 1 to A. Okay, for simplicity I will run from 1 to A, and the next section I will run backwards from 2 to A, because I only want one term in this one here. Well, if we have 2 terms, it's gonna be quite difficult. Okay, we discuss about it later. Okay, not in this lecture, maybe in the next lecture, maybe in the classroom. Okay, but anyway, with these 2 subsections, then we have 2 expressions of virtual bending moment, of course equilibrium, as we need that. The left hand side here is valid between 1 and A, 0 to 2L. That 1 is valid from 2 to A, 0 from 2L. Okay? Then, since we have 2 sections for the virtual bending moment, it is unavoidable that we need 2 sections of the real bending moment to match them too. Okay? Then, as usual, you may argue, and I cannot disagree, with this beam, once we calculate reactions, of course equilibrium, those 2 reactions, then we only need one function for the bending moment to describe the whole thing from from 1 to A to 2. However, we cannot put in the integration for the internal work done. Therefore, we have to run the same x as we did with the virtual bending moment function. So in this case, I have to use that, and that will be valid and time between 1 and A, meaning it length 2L, okay, and work out with equilibrium. Then also that one is from 2 to A, again using the same direction as before, with the same as the virtual cases. Then the expression is like so. Therefore, this one here we have to match with this one. This one here will match with this one. And then that sigma signify you have to do that one combined with that one. That expression is actually coming from this pair. Okay? That one go there, that term. That term go there, that term. The second one come from these two. That one go in there, we get here. That one get in there, we get here. Okay? I just take out 1 over EI because since it is all 1 over EI. Okay, so the expression is not more complex than it already is. Then of course we just have to times it in, integrate according to the limits, then we can get to the answer. Just cut off the details, okay? Then we end up with that expression. Same argument, 1 star is not 0. Therefore, delta A must be equal to that 11 over 6 with the expression. The same argument, since 1 star we put it downwards and the work done here is positive. So it means that delta has to be on the same direction with 1 star. So since 1 star is downwards, delta in this case will also be downward, and we get our first answer. The second part is try to find the bending moment, try to find the virtual bending moment for the angular displacement. Again, we then have to apply the bending a moment 1 star, a virtual moment 1 star at point A. Which one, in this one we put in clockwise rotation. Okay, same way again from 1 to A and from A to 2 or 2 to A, depend on how you define your x, is not the same function. Therefore again we have to separate them. Find reactions as usual. Then find the virtual bending moment for the left hand side 1 to A. Then we get this expression. Then on the right hand side from 2 to A we get that expression again with equilibrium. Now we already have the bending moment for the real force, so we don't have to repeat that calculation. We could just use the old expression again that we already have. Okay, again matching from 1 to A with from 1 to A, matching 2 to A with 2 to A. Then we have that expression. Again, this term come from 1 to A and this term come from 2 to A. Expand the term, integrate them, substitute the limits, then we have that answer, we have that value from the integration. Same argument, 1 star is not 0, so theta must be equal to that 13 over 12 WL cubed over EI. What does it mean though? This time we get minus. Okay, again this is about work done. Imaginary, still work done. So if it minus, the work done minus mean the moment and theta must go the opposite way. Okay, we apply 1 star, the moment 1 star clockwise. Therefore theta A, which means going against that one, it has to be anti-clockwise. Okay, that is all it means, plus minus. So I emphasize myself, the direction, as long as it's on the same line of what we want to know, is fine. Okay, up, down, anti-clockwise, clockwise, doesn't matter. If the delta go with the force, it's positive. If delta go against the virtual force, then it becomes negative. If theta rotates the same way with virtual moment, then it's positive, the work done positive. If the theta rotates against your virtual moment, that expression will become negative. Well, enough said. So these are the two examples, or the two answers for example number 2. Let's summarize what we have done for today. We first discussed about the principle of virtual work. I actually left out quite a lot of proof because actually it has been proved before in the previous lecture. The step of proof, the idea of proof will be on the same line. Okay, so if you want to revise on that, you should look at the previous lecture, the introduction to the energy method. Now, once we form the expression for the virtual strain energy, then we can actually use it and see the example on how we calculate deformation by bending moment using the concept of virtual work. There will be 2 in 2 system. One is to calculate with lineage displacement. Then we apply the virtual force 1 star. If we want to calculate the angular change, the slope, then we apply the virtual moment 1 star. And of course, we know how to interpret the result. And this will conclude the lecture today. Thank you very much.